Hello, how are you? Today I'm going to talk about another data structure, a heap, which is actually going to be a tree, but stored in a way that makes life easier for when we want to work with the tree. So we're looking at trees, and in fact, I'm going to keep looking at a binary tree. And I want to represent this has a structure called a heap. Now, heap is a weird name. It came, as you can see from what's on the screen here, from J.W.J. Williams in 1964, because he wanted to set up something called a heap sort, and this was the thing that would make it work. Now, I'm going to use a binary heap, and a binary heap is just a binary tree with two special properties. The heap is as complete as possible. In other words, in this tree over here, we can't have this. It's not complete because there's no right child of the first node. Over here, there's no left or right child of the second node. These violate the two rules. It's got to be complete as possible, and we fill in a level from left to right. Now that makes it easier to store, because if you do that, then the second law, is that every value in the node, which I'll call the priority, is greater than the values in its children. So there's a heap. 58 is greater than 41 and 39. 20 is greater than 41 and 30 is greater than 41. And 10 is greater than 39. Notice there's no order in this. 20 is here and 30 is here. In most of the binary trees you've looked at, you would see 10 over there. The only order is that each value is greater than its children. So here we have the way we're going to start. That heap up there will be stored the first level, then the second level, then the third level, and we'll keep going and going. Why would we do that? Well, let's look. The left child of node 0 is node 0 plus 1, 41. The right child of node 0 is 2 times 1, which is node 2. But does that work for the rest? Let's try the left child of node 2. According to this, it should be 2n plus 1. That's 5. So this is 2. 0, 1, 2, 3, 4, 5. So 10 should be it. Well, what do you know? 10 is it. And if you try any of them, it's going to work. Now, what about the parent? Well, 0, 1, 2, 3, 4. This is 5. What's the parent of 10? Well, the parent of 10 should be in 11 over 2, which is 5. The parent of 5 should be in 5 minus 1, 4 over 2. So the parent of 5 should be in the second place. That's where it is. Remember, we're starting to count at 0. What about the parent of 4? Well, 4 minus 1 is 3. Divided by 2 is 1. So the parent of 30 should be in the first element of the array. And that's where it is. So the person who thought this up was quite clever. It means basically all those all those pointers you like so much are not there to do this particular problem. Now, I just wrote this out for the fun of it. You can think of the tree as having the first level is node 0. It has children 1 and 2. 1 has children 3 and 4. 2 has children 5 and 6. 3 has children 7 and 8. 7 has children 15 and 16, and so on and so on and so on. Now, what about how do we work with this? Well, getting the node with the highest value is trivial. You take out the first node. Because remember, it's greater than its children, and its children are greater than its children, and so on and so on. Adding a node is an order log n operation. What we do is we place the new element at the very end of the node. And then we do what is called sifting it up. What this means is that every time it's smaller than its parent node, we exchange it with its parent node. And we keep doing this until we get it up to the top, get it to the place where it's supposed to be. Now that exchange works because if you remember, the parent node is greater than its children. So if we move something greater up, then it's going to be greater than its children. It's greater than the other child because it's greater than the parent was. Now, I wrote a little program to test this because I wanted to make sure it worked. I created a bin heap, and my bin heap has 2 items in it. It has nodes, and the nodes have a privity, which I use for priority, and a name. And what I did was I have a store that's just an array for all the nodes. And I have a next to fill, which starts at 0. That's the first empty element, the place where I'm going to put the nodes, the next node, whenever I have one that I'm going to put there. Then I have, that was it. That's all I needed. Then I started writing methods. So the add method, you can look at this. I think it works. I had a little trouble changing a few things here and there, but I think I got it. Let's hope. And I wrote a very simple print routine there, which again, I don't think is that bad. They seem to work for me, but you know, anything could happen. I can't seem to get this to be straight anymore, so you'll have to watch me tilt to one side. Now, I tested it so trivially. I just threw things in there. And it worked, so I hope it works for you. And if it doesn't, well, we'll keep trying. Now, that's the easy one, removing the node with the highest priority. What we do is remove it, but that leaves a hole. We're taking out the first node. So what should we do? Well, we exchange that node with the last node. We take the last node up to the top. And by doing that, we are ready to try to put it in place. So we do it sifting down. We exchange it with its largest subchild, largest child. We know the largest child will be greater than the smaller child, and we know that everything below that is, at least the next level down, is less than the node we promoted. So it keeps the heap property. There is one little trick. I found out after running it that I have to do something with that final node. So what I did was I gave it a huge negative priority. Otherwise, it exchanged with whatever the old priority was down there. And I couldn't let that happen. And not doing this would have meant a lot more if statements. So I thought this worked better. And you can see the program here. And it's all there. What I did was I got this program running with that, and it seemed to work. Now, this debugger might not be the same as with this. I guess it will be. And I'm intending to talk about the debugger possibly tomorrow so that you can have some help figuring out how to do debugging. The debugger works beautifully. At least for me it does. Now, the problem I have is I have two different sort of files running here. And this one has the word job name in it. And I don't think that's the one that I wanted. Yes, the one up here. So realize that this trace works for the second program that's on there. It was an earlier attempt. I didn't like it as well. For one thing, it was just too much. And I managed to simplify it. But you can see that sometimes the first one doesn't look too well. And that's it. Now, of course, as I usually do, I'd like you to do something with this. So I'm putting in homework 15. You're going to be scared because it again has the idea of putting in processes and see how fast they work, how much they wait. However, this time, you only have one queue. And the queue is going to be a heap. And all you have to do is take out the top of the queue and use the function that removes, which will put everything else in the right place. So taking out an element to put it in the CPU is quite easy. Otherwise, you'll have the same outline you had for the other program. You will have initializations. You'll read in all the processes that you have to read into a vector, and you'll set the time to 0. And then, while you're not done, you'll do 3 things in the while loop. You will find out which processes arrive at that time, and you will put those in the queue. Then you will see if anybody is in the CPU. If a process is in the CPU, you'll take it out, add to its time used, and either it will leave the system or it'll go right back into the queue. And finally, you'll pick the next element to go in the queue, which is the top of the queue. And you just remove. And then you'll add 10 to the time, and you'll just keep going. You'll keep going until your queue is empty. And then you will print out the results. You might print along the way to see how it's working. Now this time I want the results in the table. I'm not asking for the average. I'm just asking for the table. I'm not even asking for the waiting time. All I'm asking for is how long it was in the system and what priority it had. There is one slight quirk. Maybe you won't call it slight. When programs come in and they have low priority, they can get stuck. They can get way back in line and never get out. And we don't want that to happen. So we play a game. We say, if you're waiting and I pick somebody else, I'm adding 0.5 to your priority. So every time I pass over you, I give you a little boost in priority. That's for every element in the queue that isn't chosen. So eventually, if I keep doing that, you'll get to the highest priority, you'll get a higher priority than anybody else, and you will get to the top of the queue. Now, this is a common method of allocating queues. What it does is allow to put people in categories, which I don't claim is good. However, the people who run computers like to have different categories, so maybe they can charge people different amounts of money. If you want to go real fast, they'll charge you more for the CPU. But if you're willing to go slower, they'll charge you less. Now, this is a commercial, people. I'm not doing it, and we don't have computers on campus that do that because we don't have them that big. In many huge colleges, they have different priorities for different groups. So a research group would have a high priority, whereas an introductory class would have a low priority. And that way they think they're helping the thing they want to push the most, the research types. Or a department might have a higher priority than another department. Or the administration, the president's office might have a higher priority than the other departments. But many colleges do use a priority system. It makes it, it's a perk, I guess, of being an administrator. And we're just imitating the way it works. I'm not endorsing it, and I don't want to be accused of not liking equality. I think I'd like to get in and go as fast as anybody else in the system, but this is a real system, a kind of system that is there. Well, that's it for now. I'm going to post the notes. Under notes, there'll be notes 11. I'm going to post the data file, and I'm going to post the last program that I wrote of this. And you're going to have to modify it because the node's going to be different than the node I have in mind. But that just means changing the node. Not much else is going to change, to be honest with you. You will have to, when you're reading, you will have to read a little differently. But basically, you can use most of what I have. So that's it. I'll see you later. And